Good evening, students.
Good evening, ma'am. Good evening, ma'am.
Good evening, students. I believe all of you have settled down. Sorry, the mic was off. Good evening, students. Am I audible and visible to all of you now?
Yes, ma'am.
Yes, ma'am.
Okay. Should we start or we have to wait for someone?
Now we can start.
Okay. So can somebody tell me before we start, can somebody tell me what were the limitations of Mendeleev's periodic table? Can someone tell me the base, what were the defects or the drawbacks of the Mendeleev's periodic table? Do you remember we did this in the last class? Ananya, do you remember?
Yes, ma'am.
What are they? Please tell me. One or two, whatever you remember now.
One second, I'm opening my notes.
Okay.
Are you asking the demerits?
Yeah, I'm asking the demerits.
Couldn't find the fixed place of hydrogen because it was both alkali and a halogen.
Right. Okay, I'll now quickly go through the defects because see, Mendeleev, this chapter, as I told you, is to some students, it may sound pretty theoretical. but definitely it carries 2 to 3 marks directly in your exams in the form of reasoning question or asking you to write a certain facts about Daubigny or Newlands or Mendeleev. This is called as, these three are collectively known as earlier classification of the elements. So from this section, we may expect any of the questions, maybe a reasoning or a descriptive question. So why to give away your so easily available marks? As we have done the chapter 1, which was having lots of numericals, lots of questions were there, right? So I will appreciate if you can understand the importance of this chapter. More importantly, everywhere this chapter is practically used. We will pick up the, whenever you talk about chemical bonding, the next chapter in your books, you will be talking about the periodic table, position of elements and blah, blah, blah. So please do a regular and a good practice of this. So one thing which Shweta correctly said, that the position of hydrogen was not correctly assigned. Number 2, isotopes were not given separate places, although they have different atomic masses. Then this was an exception which I told you, and which is there in this blue colored bar, that cobalt and nickel, their position should have been swapped. 58.7 comes before 58.9, but in Mandeley's periodic table, the order is reversed. Why? Because of the similarity in properties, right? Then this we have another defect, that elements with different properties are placed together. As you can see, manganese and bromine, they are having entirely different properties. One of them is manganese is a metal and bromine is a non-metal. Manganese is a solid, bromine is a gas at room temperature. Still, they are placed in the same block, right? This we have discussed, that hydrogen was not given a satisfactory position. After that, we move to modern periodic table, where I told you that modern periodic table, 4 elements were added later. As a result, the 7th period, which was incomplete till 2018, became completely filled, right? So this was we discussed in the last class. Now moving to today's class, can anybody apprise me what are metals, non-metals and metalloids quickly?
Ma'am, metals lose electrons to gain stability.
Okay.
Non-metals gain electron to to gain stability.
Okay.
And metalloids have properties of both metals and non-metals.
Correct. Metalloids, see, please pay attention to this periodic table. Metals and non-metals occupy the extreme ends of modern periodic table. Deliberately, the lower half, the F block, is not there in this picture. It is just there to tell you that on left-hand side, what do you find? Just focus on one element, that is sodium. And sodium is a metal. This we understand from class 10th studies, right? Because sodium, as Shweta has correctly said, gives away electron. Whereas chlorine, which is placed on the extreme right-hand side. In fact, the second last column, you can identify chlorine, right? So one is a metal and other one is a non-metal. Here it is chlorine, right? That makes us believe that metals are placed on the left-hand side and non-metals are placed on the right-hand side. The elements drawn in, say, orange pinkish type of a box: boron, silicon, germanium, arsenic, antimony, tellurium, and acetine. They are believed to be metalloids. They show some properties. Please remember, Shweta, your definition was correct, but except for the fact, we have to remember the metalloids show some properties of metals and some properties of non-metals. 1 mark question is usually asked, that name a metalloid or identify metalloid from the given 4 options, right? So what we can say about metalloids is that metalloids show some properties of metal and some properties of non-metals, right?
Yes, ma'am.
Okay. Now we will talk about another term which is very often discussed and asked. What are alloys? We'll focus on variable valency later. Before that, let us find out what are alloys. So these are the certain terms which I have picked up from your books, which during the chapter are used here and there without any explanation, assuming you were taught in class 9th or 10th, and they may still be not so clear to you. So can somebody tell me what is an alloy?
Ma'am, it is a mixture of elements.
Okay. The more appropriate definition of alloy is mixture of one or more metals and non-metal. See, usually non-metal do not form alloy alone, but metals do form. Have you heard about what is a brass, bronze, dental alloy? Can somebody tell me what is brass? What is bronze? Just say we say that somebody has won a bronze medal in the Olympics, or our team, school team won the gold medal, silver medal, and the bronze medal. What is brass and bronze? And then we
Ma'am,
have,
brass is the alloy of copper and zinc.
okay. And bronze is alloy of
Copper and tin.
copper and
Tin.
tin. Are you saying tin or something else?
No, I said copper and tin.
Okay. Correct. See, when you refer to different books, you will get different composition. Since alloys come under the category of mixtures, their composition may be varying, right? Like if you talk about stainless steel, can somebody tell me the difference between stainless steel and steel? I'm not talking about the composition, I'm just asking, what do you understand by it? Steel is one of the material which is widely used in making utensils at our home, right? Most of the time we use utensils made up of steel. So what is a steel? See, steel is also a alloy, right? Steel is alloy of, the main component of steel is iron. Whatever we are using as utensils is made up of iron. Then it has chromium. Then it has one of the important things about steel is that it can have a variable components and can have any number of metals in it, right? Basically, the two major components which must be there in steel are iron and carbon. It is a classical example of an alloy in which there is a metal. All of us know that metal, iron is a metal and carbon is a non-metal, right? Now, what is stainless steel? Stainless steel is a variety of steel which does not stain. Have you noticed that the whatever type of utensils you are using at home, which are made up of steel, they do not stain. You cannot find a stain on them. Have you noticed it or not?
Yes, ma'am.
Okay, that is why it is called as a stainless steel. So it is having some percentage of manganese in it so that it becomes stainless steel, right? We do not need to remember the composition of a steel or a stainless steel, but if somebody asks you to pick up the alloy of iron, one of the answers can be steel or stainless steel. They are more or less same thing, except for presence of one or two elements in them, right? Now, talking about dental amalgam, what is it? I think amalgam was there in class 10th in the extraction of sodium hydroxide, sodium chloride, something like that. Chloralkali process.
Yes, ma'am.
Okay. So tell me, what is an amalgam?
Amalgam is
Contains
the alloy of
mercury.
mercury and one more metal.
I didn't get you. Ritika, can you please repeat it? Ritika and then one more student was saying. So let us begin with
Yes,
Ritika
ma'am.
and
I said that any alloy that contains mercury is called amalgam.
okay. Pretty correct definition. It is that alloy of mercury with other metal, right? We cannot use the word element here. Non-metals do not form amalgam, right? So amalgam is this. Now we say dental amalgam or a silver amalgam. That means silver and mercury are mixed in a certain ratio and they are used as a dental filling. Remember, earlier it used to be, the dentist used to use mercury amalgam silver amalgam to fill the cavities in the mouth of their patients. But later on, it was discarded. Now they use something else, which is bit synthetic and maybe more cheaper and more useful. There are two metals which do not form alloy. That is often asked question. Metals do not form amalgam. Metals which do not form amalgam are I'll give you the answer. PT is the symbol of, can anybody tell me?
Platinum.
PT is the platinum, correct. Platinum and iron are the two metals which do not form amalgam with iron, with the mercury, sorry. Is it clear? Okay, moving on to the next, which I wanted to confirm before we proceed. What do you understand by variable valency, right? And number two, if you know what is a variable valency, if I write FeCl3, FeCl2, CuCl, and CuCl2, can you name these compounds? For this, first of all, you need to know what is variable valency, right? And then what will be the name of these four compounds? Any idea, students?
First one is ferric chloride. Second one is ferrous chloride. And then it is copper chloride and cupric chloride.
How can the first one is copper chloride? Both of them, to me,
Sorry,
both of them
ma'am.
are, oh, yeah.
No, ma'am, I said the first one is copper chloride and the second one is cupric chloride.
You said the first one is copper chloride. Am I correct, Ria?
Yes, ma'am, but I think I was wrong. I think it is the first one is cuprous chloride and the second one is cupric chloride.
Yeah, that's correct. Shweta, Ritika, and Ananya, are you clear about this concept?
Yes, ma'am.
How to use the us and ik? Us is always used for the lower valency of the same element, right? And the ik is used for the higher valency. That is good that all of you know about it. I was just rechecking what you remember and what you do not. Now, as we understood in the last class, that total 118 elements are known at this time. But what happens is that, like I am teaching you here, some other teacher might be teaching other students somewhere else, right? And before exams, all of us need to complete the syllabus, have revision and practices. Otherwise, there will be a lot of confusion and collisions. Similarly, when scientists work in isolation in different countries, like this is an example given in your NCERT books, that atomic number 104, the American and the Soviet scientist, Soviet, you can say Russia, sort of Russia. Soviet Union was a earlier terminology which was used for a certain group of certain nation. So roughly we can say Russia. So Americans and people or the scientists from the Soviet Union discovered the element with atomic number 104 together at the same time. Together does not mean working together, at the same time. And the Americans called it as Rutherfordium, and the Soviet people named it as Khrushchetovium. Now, why you are given a single name, so that there is no confusion. I know that I'm talking to Ananya or to Ritika or to Shweta or to Riya, right? If all of us, the millions and billions population is given the same name, there will be a lot of communication gaps, and which will be very difficult to cope up and complete that. So IUPAC, that International Union of Pure and Applied Chemists, right? What it did, it gave certain rules for writing the name of the newly discovered elements. It applies only to the elements which have atomic number more than 100. Till 100, no rules apply, right? Above 100, this rule is used to name the newly discovered element by the scientist. What does this rule say? That you have to...
Ma'am, can you show the previous slide just for a second?
Yeah.
Yes, ma'am.
Okay. So for writing the name of the elements having atomic number more than 100, they gave every digit from 0 to 9 a particular name and an abbreviation or a symbol. So for 0, they called it as nil. Nil, I don't know in which language it means. Nil means 0, which does not have anything, right? Then they said 1 is read as un, U-N, un. 2 is read as B, un, bill, they called it as B. 3 is called as tree. 4 is called as quad. 5 is called as pent. 6 as hex. 7 as sept, not hept, sept. 8 as oct, and then 9 as in, right? And if you notice the abbreviation or the symbols, they have picked the first alphabet of each symbol. From nil, they picked up N, from un, they picked up U, and so on. Is it making sense to all of you?
Yes.
Yes, ma'am.
Okay. So suppose if I have to write the name of the element having atomic number, let's erase this example, although you can write that also. The rule says what we will do, we will write the symbol of the symbol or name plus IUM. They read it as EM. So if I have to write the name of element having 108 atomic number, so what I have to do? For 1, I will be writing on. For 0, I will be writing nil. For 8, I will write oct. And then I will add IUM. So what will be the name of compound element? Sorry, this will be un, nil, oct, ium. Right? And if somebody asks me,
Isn't it based on the valencies though?
are you saying anything, Riya?
Yes, ma'am. I thought it was like from the previous explanation, I understood as the name was based on the valencies.
No. See, I think you are don't mix. These are two separate concepts. See, I made you recall the concept of variable valency because while they are explaining periodic table, they have used the word variable valency. And if the student do not recall this terminology, they are at loss. So I thought I think I told you in the beginning of the class that we will be, first of all, revising few names or the concepts which are written there in the periodic table chapter of the periodic table, and they are used randomly here and there, no specific place. These concepts these concepts are nowhere related to the concept of modern periodic table. But when I or anybody else or the book is explaining, they are using these concepts very frequently. And some of the students might have forgotten, or some of them might not have been taught. So I thought it would be wise, instead of having a break at every step in explaining them, it's wise to put it at one place, right? I think it makes sense to you, Ria?
Yes, ma'am. I understood. Sorry, ma'am.
Okay. No, it's okay. That's I still appreciate, or rather, I like that the students asking questions. That means that you are understanding something, right? You are here to learn, and I am here to make your concepts more clearer. So this is the rule. I believe it is clear to all of you. I was telling you that if I have to write the symbol of this element, what I have to do, I will pick the abbreviations. For 1, I will be using U. What will be the symbol of this element? Yeah, right. Un, nil, octium. So UNO will be the symbol. Like we just said, platinum is a name of element. It is represented by PT. Iron represented by Fe. Similarly, the element having atomic number 108 will be having the name as un, nil, octium, and its symbol will be UNO. Is it clear to all of you?
Yes, ma'am.
Yes, ma'am.
Okay. Okay. Now this is a screenshot is again taking for from your NCERT book. From here you can read them. You can practice. You can take any one of the element and write its name. Usually, I have seen that the school teachers give a 1 mark question from it, like 100 and like the write the symbol of 108, 112, or anything. And usually the digits are from, or rather the number is from between 100 to 120, not more than that, because the scientists have discovered only till 118, right? So you can just remember this and score good marks in this section. Now moving on to the modern periodic table and its numbering. I believe we discussed what is a group and what is a period in the last class. Just let me refresh my memory. I just forgot it. Are we clear what are the groups and what are the periods?
Yes.
Yes, ma'am.
Okay. Now, once we have groups in a hand, we understand that the top to bottom, horizontal rows or horizontal columns are known as groups, right? Then we have to number them. One of the way is to number them as 1 to 18 as shown on the screen. There is another way of naming them. Are you aware of that? I'm waiting for your response, students.
No, ma'am.
Okay. See, this numbering is, although they say they have discarded, but still many a times the question is asked. See, 2 years ago, they have asked the question based on this nomenclature or the numbering of the groups of modern periodic table. This group 1 and group 2 are named as group 1A and group 2A. From group 13, I'm just leaving those from those in between. Here they are named as 3A, 4A, 5A, 6A, and this one is the 7A. And the last one is group 8. Is it clear?
Yes, ma'am.
Yes, ma'am.
Okay. And the groups in the center from 1B. This is 1B, this is 2B, this is 3B, 4B, 5B, 6B, 7B, and then 10, 11, and 12. They are collectively called as group 8B. Sometimes this group 8 is called as zero group. Is it clear?
Yes, ma'am.
Okay. But nobody asked me why it happens. Why are we calling certain group A and why are we calling certain group as B? If you have not asked me, then I'm going to ask you. Any answer? This is a better version of same thing, where you can see 1A, 2A, then 3B, 4B, 5B, 7. Sorry, I think I made a mistake here. Yeah. Let's delete it and we will do it by that one only. Just 3B, 4B, 5B, 6B, 7B. Then we have 8 and then 1B, 2B, and then this. Why do we have a group as numbered as A and B? Any idea?
Because they're classified into different types of elements, like what to say, noble gases, like that.
No. We will just take up one small activity, or rather we will write the electronic configuration of element, let's say with atomic number 11, 17.
Ma'am, but zero group is all noble gases, no, ma'am.
I didn't understand your question, Ria.
No, ma'am. From the table that you just showed, isn't zero group like all noble gases?
Yeah,
Okay.
I'll come back to that. I'll explain it to you. 11, 17, 23, and then let's say 62. I believe all of you understand or all of you know how to write the configuration of these elements according to Aufbau rule. right?
Yes, ma'am.
Now, can you
Yes, ma'am.
quickly write it down? Then with the help of that, we will understand how to assign group, period, and block to modern periodic table. And this will clarify why certain groups are numbered as A and while others are numbered as B. I'm waiting. Once you are done with 11, 17, and 23, let me know, please. Can somebody tell me for 11?
Ma'am, 11 is sodium, so it is 1s2, 2s2, 2p6, 3s1.
Correct, Priya?
2p6. Yes, ma'am, 2p6 and 3s1.
Okay. Now, Ritika, 17 is?
Ma'am, it is 1s2, 2s2, 2p6, 3s2, 3p5.
Correct. Now, Shweta, 23.
1s2, 2s2, 2p6,
Yeah,
3s2,
yeah,
3p6,
right.
4s2,
Yeah,
and 3b3.
correct. Now, let me explain what is the reason that we study the chapter structure of atom first, followed by the periodic table. Now, if somebody asks me, although we know this is sodium and this is how and in which group it is placed, I have not given you the tougher ones. In exam, they usually ask for 47, but that would have taken a lot of time for us or some more minutes for us. So I thought we will begin with this easier one. Now, if I talk about the first one, that is atomic number 11. Now, since last electron is entering into s orbital, as all of you have correctly written. So the element with atomic number 11 will belong to S block. Where it is, that I will just show you. Right? What about its period or group number? For that, we must understand the basic structure of the modern periodic table. I'm drawing a rough sketch of that. Please don't go by my drawings. We say this one is group 1, 2, and then we have 3 to 8, 3 to 12, and then we have 13 to 18. Let's hold that A and B for the moment, because after understanding that, this particular concept, that will become easier for us to know, right? And then we will understand where are the blocks placed. We say the block, this is the S block. This one is said to be the D block. And this one is said to be the P block. And below the modern periodic table, the group of 14 elements in 2 rows are placed and they make the F block. I'm repeating myself that we number modern periodic table groups from 1 to 18 left to right. F block is placed below the modern periodic table's main body. The first 2 groups comprise of group 1. First block, that is S block, comprises of 2 groups, 1 and 2. The second block is D block, which comprises of group number 3 to 12. And how many groups will be there in D block? How many? S block will have 2 groups, 1 and 2. And this D block will have 3 to 12. How many groups?
9 groups.
10. 3, 4, 5, 6, 7, 8, 9, 10. 11,
Oh,
12.
yes, ma'am. Sorry.
It's okay. So this will have 10 groups, right? Similarly, 13 to 18, how many groups? They are 6.
6.
6. Now, what do we connect these numbers to the periodic, to the configuration? Maximum number of electrons in S group, S was 2. It can either have NS1 or it can have NS2 configuration. Making sense or not?
Yes, ma'am.
Yes, ma'am.
Okay. So what we can say, S block general configuration will be either NS1 or NS2, or collectively we can say NS1 to 2. If you look at the configuration, this you can do it at your own. Lithium, sodium, potassium, rubidium, cesium, francium. Atomic number 3, 11, 19, and then I believe it's 37. If you write the configuration, what happens? 1s2, 2s1. Sodium, you people have just finished it off. In last, what you are getting?
3s1.
3s1. Here, similarly, you will be writing and you'll be getting 4s1.
4s1.
Here you will get 5s1. Here you will get 6s1. So from this, what we can say? The general electronic configuration of group 1 elements is NS1.
Ma'am, I have a doubt.
Yeah.
Is like, are only these elements in the S block? Because you also gave us vanadium and that ends in 4s2, or do we write 3d3 at the end? So does that go into D block?
I didn't get you, Ria. Can you just please?
No, ma'am. Yes, ma'am. Like you asked us to write element 23, which is vanadium, no, ma'am?
Yeah.
Yes, ma'am. So my doubt is, like, after 3p6, do we write 3d3 and then 4s2, or do we write 4s2 and then 3d3? Because
Yeah. I'll come back to that in a second.
yes.
Let us finish S block, P block, then we will come to D block, Ria. Your question is valid, and many a times this confusion occurs. I'll clarify that also. That was all. That's a good question. That was in my agenda of teaching also. So is it clear that how do we write the general electronic configuration for a block or for a group? What is the meaning of N? It signifies number of shell, right? Now, if I write, so that means it belongs to atomic number 11, belongs to block S, and since it has got one electron in its valence shell, that means its group number is 1. Now, how do I find its period number? And have I taught you that or not? The relationship between orbit and orbital configuration. How to convert an orbital configuration into orbit configuration. Have we discussed that or not? Ritika and Ananya, please reply.
Yes, ma'am.
Okay, is it, I think Ria is a new student, or at least I'm seeing it for the first time. Ria, do you know, or is anybody having? Yeah, Ria, please speak.
Yes, ma'am. Like today is my first class.
Yeah. So for benefit of Ria and just a revision for everyone, we write the configuration as 1s2, 2s2, 2p6, 3s2, 3p, sorry, 1s2, 2s2, 2p6, 3s1. So if this is an orbital configuration, how the electrons are being filled in the orbital. If somebody asks me how they are filled in orbit, I will not ask you and I will not suggest you to go back to Bohr-Bury's rule. You have to get it from here itself. Look for the data or look for the digits which are having the same principal quantum number. 1s2, that is its prefix is 1. That is used only at one place. That means my first orbit will have 2 electrons. Similarly, the second orbit, it has got 2s2 and 2p6, 8. 2 and 6 will make it as 8. So second orbit will have 8 electrons, and 3s1, that will make it as 1. Is it clear to you precisely, Ria?
Yes, ma'am. It's clear, ma'am.
Okay. Now, how do I find a period number? This is one way. Another way is that highest quantum number. What is the highest quantum number in this? In case of 11. One is 2, 2 is 2, 2p6, 3s1. The highest principal quantum number is
3.
3. 3. So its period number will be 3. So if I enlarge this periodic table over this screen, you can, or I will place it on another slide then. Here you can see where is sodium. This is S block. This is group 1. This is period 1, period 2, and period 3. You have correctly identified its position in the modern periodic table. Is it clear to everyone? Okay, let's talk about atomic number 17. As you have written 1s2, 2s2, 2p6, 3s2, 3p5, right? That means it's clear that its block is P, right? In block P,
Yes.
in the P block, this is the first group, boron. Boron is the first element of P block, right? So this group number is 13, 14, 15, 16, 17, 18, right? And it has got 3p5. So the configuration for the first group of P block will be, in the end, it will be P1. This is P2. This is P3, P4, P5, P6. So that means P5 where is P5? P5 is this one, which is group number 17. So this is block P. Group number is 17 and the period number is the highest quantum number, that is 3. Is it making sense to all of you?
Yes, ma'am.
Yes.
Yes.
Okay. Now, coming to atomic number 63. Not 63, before that, atomic number 23. The purpose of putting the numbers smartly was, one is S block, another one is P block, another one is D block, and the last one is of F block, correct? So if you write the configuration as all of you have written it correctly, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. The question from Ria was that should I write it as 3d3, 4s2 or this order? I will say this is the correct way. Reason being, the people who say that write it as 3d3, 4s2, what will happen? If you copy down rest of the things and then write it like this, what you will assume? It seems as if S block element.
With S block.
Is your doubt clear now, Ria?
Yes, ma'am.
So that is the reason you are always asked to fill the electrons in the various orbitals according to Aufbau rule in the same order, right? So that means this element belong to block. I believe everyone would be clear. The block number will be, or block name will be D block. Then talking about group, what I will do here again, we will just enlarge the periodic table and put the numbers, right? So we knew that this is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Valence shell configuration or the last electronic configuration has to be D1, D2, D3, then D5, S1, and I believe it will be very difficult for you to understand. Let me focus on 23 first. So that means D3 is group number 5. So its group number is 5. Now when we talk about period, then by this time, if you have done a good practice, you can simply say that highest principal quantum number is 4. So the period number will be 4. See, there are two different things. One is order of filling, and one is the other question is that how to answer this question, right? I believe it is clear to all of you. Ananya, is it clear?
Yes, ma'am, it's clear.
Clear. So I want all of you to correctly identify the group and the period of these elements. And if I talk about the point which I left here, D5S1, then we will have D5S2. Have you written the configuration of atomic number 24 and 29? Or quickly, can we write it? The electronic configuration of 24 and 29. Please do it.
Ma'am, for 24,
Yeah.
It will be 1s2, 2s2, 2p6,
Hmm.
3s2, 3p6, 4s2, 3d4.
Who said that? Shweta.
Shwet, yes, ma'am.
Okay.
And 4s1, 3d5.
Okay. 1s2, 2s2, 2p6, 3s2, 3p6. Then
4s1 and 3d5, ma'am.
4s2, 3d6. This is what 3d4. Sorry, this is what Shweta said, right? Anybody having a different configuration?
Yes, ma'am. Yes, ma'am. Instead of it should be 4s1 and 3d5.
Now, Ritika, do you agree with Shweta or Ria?
Ma'am, I agree with Shweta, ma'am.
Okay. So Shweta and Ritika here. And what about Ananya? Where do you put your vote?
Even I agree with Shweta.
Okay. So that means somehow we have missed a basic concept. For exception of atomic number 24 and 29, we say that nearly stable, nearly rather not stable, nearly half-filled. Orbitals are less stable. Nearly half-filled or nearly fulfilled. Orbitals are less stable than exactly half-filled or exactly fulfilled. See, the correct configuration is the second one, not the first one. We have to understand that here we are writing 4s2, 3d4. The configuration, if I write it as 4s1, 3d5, what happens? The energy becomes almost equal. They become more stable. They are now exactly half filled. 4s2 is the maximum, 2 is the maximum, half is 1. 3d5 exactly half filled. Both of them have become exactly half filled. Otherwise, this one was fulfilled and this one was half filled, nearly half filled. Similarly, if I write it for 29, according to above, we should be writing it as 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. But this is incorrect. It has to be
4s1 and 3d10.
Yeah, it has to be 4s1, 3d10. That is how this one will become exactly half filled and this one will become exactly fulfilled. Now, to the students which either have forgotten or somebody might have missed in teaching to them, that this concept, there comes another question. Where should I apply it? I will give you the example. Where we have to apply this judgment. This one, please remember, that will be easier for all of you to remember that you have to apply it to only 24 and 29. Nowhere else. Please put it down in your notebooks that you have to apply this logic only on the chromium group and the copper group, that chromium, molybdenum, tungsten, seaborgium, copper, silver, gold, Rg, I don't remember. Is it clear? Otherwise, what happens if I write the configuration of, let's say, fluorine, atomic number 9, 1s2, 2s2, 2p5. The students come to me asking Ma'am, can I write it as 2s1, 2p6? This question is specifically to Ria. Can we do so? If we do so, why? And if we do not do so, why?
No, it's for fluorine, ma'am.
Yeah, it's fluorine.
Okay, 1 second.
No, my question is not to identify this element. My question is, we have just learned that nearly half-filled and nearly full-filled orbitals are less stable than exactly half-filled and exactly full-filled orbital. Therefore, if I apply the same logic, we have this 2s2 and we have this 2p5, right? 2s2 and 2p5.
Yes, ma'am.
If I shift one electron from 2s to 2p, it will become 2s1, 2p6. Should I do
And
it?
it is
Or should I?
technically more stable, but it doesn't work that way. I don't know why even.
Okay, that is the reason I'm explaining it to you. Technically correct, incorrect, there is a reason to it. I will explain to you right now. But we have lots of syllabus to cover, but instead of that, and just instead of doing where should we see, sometimes it's easier to remember where I have to do rather than having a huge list of where I don't have to do, right? Simply put it here only. The answer lies in atomic structure and the electronic configuration. I'm not too sure whether you are taught in this way or not. When you talk about orbits and orbitals, right? What is the shape of an orbit, if I can ask you? We draw it circular, right? But is it the real
Yes.
shape of an orbit?
No, ma'am. Orbits are actually imaginary.
We believe orbits are not spherical, but still we draw them spherical because it is convenient to draw. Please put it in your mind. It is convenient to draw, therefore we still continue to draw them in a spherical manner, but they need to be made as elliptical. Again, I'll say still, my drawing it may not be very good, but please try to understand what I'm trying to say. Assumingly, I'm just trying to draw them as elliptical as possible for me. Let's assume this to be the nucleus, right? But before I talk about it, can anybody tell me, if I ask you to draw an orbit and orbital in an atom, will you be able to draw that in the same picture?
No, ma'am.
Anybody else? Ritika, what do you say? What is your take?
Ma'am, I'm not sure, ma'am.
Okay, till now you are able to understand what I said, that you have to use an exception at 24 and 29. I'm specifically
Yes,
asking this
ma'am.
question to Ritika, Anandya, and Shweta. Look in your NCRTs if you have any doubts, right? Maybe you have not, somebody might not have put so much of a focus on it, but that's a fact. For 24 and 29, they are the two elements, copper and chromium, which are very oftenly asked, or the elements following that. Copper ke niche silver aata hai, that 47 or 29, they will have the same configuration. They will be having, say this, that 3D and 4s, then it will be 4D and 5s, right? Now, give me a moment. I'll bring a piece of an onion to show you how can you relate where is an orbit and orbital. Give me a minute. See, I'm trying to recreate what an orbit or an orbital look like to you. They are in two different planes, right? If orbit is in this plane, assume it to be a ellipse for the time being. Then suppose it is a fourth orbit. I believe all of you can see this. Can you see
Yes,
my
ma'am.
hand? Okay. See, if it is an elliptical, then the nearest circle in the center will be of S. Then afterward will be the P. See, P will be outer to this, or I can say the bigger to it. Then we will have D, and F will be still bigger to it. Is it making some sense to all of you?
Yes, ma'am.
Okay. We have to understand, again, I'm repeating that we have to understand orbit and orbital are at perpendicular distance from each other. Orbit is elliptical in shape. Now, and we can assume, looking at this, we can assume that, or we can see for sure this, that S orbital will be the closest to the nucleus. This is a key takeaway from this activity. Is it clear to everyone?
Yes, ma'am.
Yes, ma'am.
Okay. So if I draw one orbit separately, if this is my let's say fourth orbit is this one. So where will be the orbitals? This will be the 4s orbital, area of 4s. That will be followed by 4p. That will be followed by 4d. And that will be followed by 4f.
Correct.
It means for the fourth shell, if it was circular, then S, P, D, and F, all electrons would have been attracted towards the nucleus by equal force of attraction. But since it is elliptical and 4s is nearest to nucleus, what will happen? The force of attraction will be maximum attraction towards nucleus. Then 4p, then 4d, then 4f. Is it making sense to all of you?
Yes, ma'am.
Okay. Now, talking about the configuration of 23. 23 was telling us in the end what we were having. We were having 4s2, 3d3. The outermost shell, whatever shell number is, the outermost shell is known as valence shell. This we all know. A valence shell or valence orbit. This orbit next to, if I number it as n, then next to it, n-1 is called as penultimate shell. Right? Then this one, n-2 is called as anti-penultimate shell. Have you been taught about it in the structure of atom chapter?
No, ma'am.
Okay. Now, if I convert, now is it clear to all of you so that I move further?
Yes, ma'am.
Okay. So when I convert that orbital configuration into orbit configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. I will get it as 2 to 8 for 3s. What I will do? 3s2, 3p6 and 3d3. 2 plus 6, 8, 8 and 3, 11. And 2. have you realized where is the last electron entering? It is not entering into valence shell. Valence shell will comprise of 4s, 4p, 4d, and 4f. This is 4s, or rather 4s we should be drawing here, which is closest to nucleus, right? This will be 3s. This will be roughly, say, 3p, and this will be roughly 3d. Then we have in this one we have 4s, 4p, 4d, and 4f, right? Please pay attention. Where is the last electron entering? Is it entering valence shell?
3D. Entering 3D.
No.
ma'am. It's entering penultimate shell.
It is entering d orbital of penultimate shell or penultimate orbit. Is it clear to everyone?
Yes,
That in
ma'am.
Yes, ma'am.
d block elements, the electron enters into n-1 d level, or it is entering into the penultimate d orbital here. Right? What should be the general electronic configuration then? It should be n-1, d1 to d10, ns1 or 2. Is it clear now? For S block, we said
Can
it
you
can
just
be.
repeat the last point? I didn't understand last point.
Okay. We understood the general electronic configuration for atomic number 11 can be written as, for group 1, it can be written as ns1 or ns2, right?
Yes, ma'am.
Similarly, for P block, we can write it as you can see, 3s2 and 3p5, they both belong to the valence shell because they are having the highest quantum number. So what can be the general electronic configuration for P block element? It has to be ns2 np1 to 5. Is it making sense to all of you or not?
Yes, ma'am.
Yes, ma'am.
Okay. Similarly, if I have to write it for D block element, coming to this element, 23, what should I be writing? This has to be, the electron is entering into D. D has total 10 groups numbered as 3 to 12, right? And the electron can be either 1 to 10. Any number can be there. Or where it will be? It will be the penultimate shell. So if the maximum quantum number was 4, the electron is entering into 4 minus 1, that is 3.
So 3D 1 to 10. Okay, ma'am. Got it. Thank you.
Got it? So that is how you have to represent the electronic configuration of the D block elements, n-1, d1 to d10, ns2. Like I have told you, the exception of chromium and copper. There you were having this as 24. Yeah, here. For 24 and 29, we have to remember that it will be n-1, d5 or d10, and ns will be 1. Therefore, in general electronic configuration of D block, we do write this. n-1, d1 to d10, ns2. Is it making sense to all of you? Anybody having any doubts? Okay. Now, similarly, 62, I'm giving you 62 for your homework. I think we started with those 4 atomic numbers. 11 was S block element, 17 was P block element, 23 is a D block and 62 is a F block element. Right? So next class, I'm going to continue this class, not leaving you right now, where we'll begin with this one, because see, again, it is a part of structure of atom. So, and if you write 62, it will take some time, right? And we will not be able to cover anything more in this class. So we'll just do that 62 in the next class. I was explaining to you that why this will be D1, D2, D3 for chromium family. I believe now this point will be clearer to all of you, that for chromium family, this CR, it will be D5S1. For manganese, which is atomic number 25, right? If I write it for 25 quickly, it will be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. So for chromium family, it will be D5S1, and for manganese, it will be D5S2. Is it clear to everyone?
Yes, ma'am.
Yes, ma'am.
Okay. For iron family, it will be D6S2, then D7S2, D8S2. For copper, it will be D10S1. And for zinc, it will be D10S2.
S2.
Right? I will tell you one more thing about this family. Do you want to note it down, or are you clear about it?
Noted, ma'am.
Okay.
I'm actually 1 second, ma'am.
Okay. I'm waiting. Whosoever said, I will just move to
Yes,
the
ma'am.
next
You
one.
can continue, ma'am.
Okay. See, I'll tell you how to remember the atomic numbers and the configuration of first series of D block: scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Remember this series: that's scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Now look at their atomic numbers carefully. Scandium, since it is 21, last digit is 1. So it will have whatever, 3D5, sorry, it will have 3D1. 22 will have 3D2. 23 we have just seen, it is 3D3. No need, I don't know, when you were writing, you were calculating, will it be D3, D4, D5? I don't remember who was doing so, but all of you must be doing so, right? So that is way you can remember that. Chromium 24 is the exception. All of us need to just put it in our memories. 3D5, 4S1. Now coming to manganese, atomic number 25. So
4
this
is
will
1,
have,
ma'am.
huh?
4 is
Sorry.
1, ma'am.
Yeah, sorry. So manganese will be 3D5, 4S2. Iron 26, just pick the 6. So it will be 3D6. Cobalt 3D7. Nickel 3D8. Copper 3D10, 4S1. That's an exception, we know. 30 will have 3D10. Does it make sense or help you in understanding it or not?
Yes, ma'am. It makes sense.
Just remember the series, because see, why I was telling you this was in exam they ask you to assign a group or a period. They put up a question that a scientist discovered, let's say, an element on the surface of moon having atomic number 80. Find its block, or more smartly, they put it as that does it resemble with the element with atomic number 48 or 47. So you have to write it for 47, 48, and 80. And then you have to show them. If you just write them that it resembles 48 as cadmium, they will not give you the mark. They believe that you must have asked your friend and written an answer. You have to write the configuration. So whosoever has not done good practice of it, please do it, right? I believe you must have done it, but again, my emphasis and request to all of you is pick any atomic number from the periodic table is with you, right? And if you want to follow NCERT's periodic table, you can. If you want to take the picture of this or take it from your recorded lesson when they are made available to you, you can take this picture because this is an authentic periodic table, which personally I have verified it, right? The purpose is you should have a proper, correct periodic table. Another thing is we must remember, we cannot remember the names of F block elements, and they are never asked. So please don't put your energies in remembering the name of F block. Till D block, it is D block 2 rows. Zinc and cadmium, they are fine. After that, please don't put your energies in remembering them, right? Please remember the periodic table vertically. That helium, neon, argon, krypton, xenon, radon, and oxygen. New elements, even I'm not too sure. Oxygen, I remember that's all, right? Then oxygen, sulfur, selenium, tellurium, polonium, livermorium. Have you heard about what are mnemonics? Have you heard about them?
Ma'am, actually, will they ask us configuration beyond 30?
Yes. I'll tell you, I'll answer your question, Ria. We know the structure of, let's say, sodium chloride. I'll take the easiest example, right? They asked me,
Yes, ma'am.
what is rubidium chloride an ionic or a covalent compound? How will I answer? This was the purpose of making a periodic table. You don't know rubidium, but if you know that in periodic table, it is placed below rubidium, right? Then you can say it will form a ionic bond like sodium chloride. Now, if I know sodium was, the valence shell was 3s, lithium, sodium, potassium, rubidium. If it was 3s1, it would have been 6s1, right? So if you have to draw the structure of rubidium chloride, like you were drawing in sodium chloride, they can surely ask for this. They will not ask you to write the configuration. They will ask you to show the diagrammatic representation of it. So what you have to do for sodium, you used to draw 3 circles. First orbit, second orbit, and third orbit. And then you say 1 electron is given to chlorine, right? But here, if you know that its position in periodic table, what you will do, you will smartly draw 6 circles, right? And then you will say 1 electron will go from here to chlorine. Is it making sense to you, Ria, specifically?
Yes, ma'am. Yes.
They are not, see, for the benefit of all the other students also, or in general, I wish to say that the questions will not be direct to you, right? As I told you that they will give you the atomic number of 80, that is of mercury, and then they will ask, will it form a covalent or an ionic compound? Now, if you know what is the position of mercury in the periodic table, you know it is below zinc, right? Zinc, cadmium, mercury. So if zinc forms zinc chloride by giving away 2 electrons, so it also has to do the same thing. Smartly, they have asked you the periodic classification as well as structure of atom. The 2 chapters and followed by chemical bonding. These 3 chapters are completely interlinked, right? They will be asking the question, the type of question will be something like that. In this chapter, we must spend enough time in understanding the basics of the periodic table. That's why I said that remember in the form of group, not in terms of periods. Till 30, you were asked to do it in class 10. Very fair. But in class 12, I'll ask you for S and P block. Don't do for D block, because D block is an entirely separate chapter in your class 12 syllabus. D and F block elements you can search on NCERT. it is there. So there you have to remember them anyways, but only the first transition series, as I have told you. Again, the purpose was to make you understand. If you remember the first one, by the time in class 2, it will be easier for all of us to learn the second one also. Because then you have to remember that F block, no one will ask them. I will tell you the reason also. You can see the atomic number 90, thorium, purple box at the bottom of the slide. The elements after thorium, after uranium, that 92, they are very, very rare. Most of them are, or all of them are prepared in the laboratory only. Their half-life periods, I believe you are not familiar with the term half-life period, but that is a way of measuring the total life of a substance. Their half-life period is in fraction of seconds. Some of them live 0.0005 seconds. So in this time span, you cannot find or study their physical and chemical properties. So therefore, nothing much is many things are not known about them, right? So you do not have many properties. D and F block is there in your syllabus in class 12, but if D block is of, let's say, 10 pages, F block is of hardly 3 pages. Most of the time they focus on the electronic configuration, which I promised you that we will be taking up in the next class. We'll pick up one last question or one feature of the periodic table before we wind up the class. That is why this F block is kept separately below the modern periodic table, the main body of the modern periodic table. Has anybody learned about it? Is it completely visible to you? Can you read the atomic numbers in this periodic table? I believe so, you can. Look carefully. After 56, barium. 57 is lanthanum. The atomic number 58 is kept here. From 58 to, this is 71, lutetium. Can you count how many elements are there? Beginning with cerium, 58 to 71. How many elements are there?
14.
14. Again, you can correlate with the orbitals. That F block has 14, maximum 14 electrons. So therefore, they are 14. Nobody asks you for the group number for F block elements. They ask only period number and the block. For the sodium, you can find out the group, block, and period, all three things. For F block elements, you will be asked only to find the block and period. Group will not be asked, right? These elements, which are placed below the main body of the modern periodic table, beginning with the cerium 58 to lutetium 71, are called as lanthanides or lanthanoids. Both the spellings and the words are same. Similarly, another set of 14 elements after radium, then you have actinium with 89, then beginning with thorium, 90 is here. Thorium 2, this is LR is lawrencium, 103. They are placed below lanthanides, below the main body of modern periodic table, and they are referred as actinoids. The reason why they are placed below the main body, you can imagine that after 57, if you insert 14 more boxes, what will happen to the periodic table? The 14 will be too much, maybe more than that. And then hafnium, you have to shift the entire 9 rows of periodic table have to be shifted more towards the right hand side of mine. So that means the periodic table will become unmanageable. That is the one reason that why F block elements or lanthanides and actinides are placed separately. One is it will become very long. Number 2, they show similarity in property. This is again an important 2-mark question. The first one we usually forget. We don't remember that because very long becomes a feature of the periodic table, right? So there are 2 reasons. If we place them in the series as they are, the periodic table will become unmanageable, right? The other thing is they show similarity in property. We'll talk about lanthanide contraction, not this year, in class 12, that their sizes are practically same. That we will learn in the class 12, right? So since they show similarity in property, they must be read together or studied together. So we place them separately in the same group below the main body of the modern periodic table. One of the reasons for having the similar properties is their almost identical size because of the property known as lanthanoid contraction. If you are interested in it, you can note down. Otherwise, for class 11th student, it is enough to understand, right?
Yes,
Any
ma'am.
questions? Any questions?
No, ma'am.
Okay, so we'll be winding the class right now, and we'll begin it with a detailed study of F block, taking an example of element 62. Again, please
Ma'am,
write.
actually,
Yeah.
Ma'am, actually, what is 57 and 89? Because it has, like, literally the elements are named lanthanides and actinides, like from what I see on the screen. So, like,
Yeah.
what are they?
Lanthanides are described here as elements after lanthanum. After lanthanum are lanthanides, and after actinium are the actinides. Is it clear
Okay,
now?
got it. Yes, ma'am. Yes.
They are placed there because this Y is yttrium and lanthanum. They show similarity in property. They have almost same atomic size. Zirconium, hafnium, below the titanium, 22, zirconium and hafnium, they show similarity in property. That we will, again, I say they will be dealing with them in class 12, chapter DNF block elements. But for the time being, your question is valid. Why, if they do not include lanthanum, why do we call them as lanthanides, or why do we call them as actinides? Again, I'm repeating that lanthanides means element after 14 elements after lanthanum. If you want to define them, there are 14 elements after lanthanum in which the last electron enters into anti-penultimate f orbital. Similarly, actinoids, 14 elements after actinium in which the last electron enters into n-2 F1 level, F level. Is it clear to you, Shweta, also?
Yes.
Okay. So we'll be beginning next class, which will be on Wednesday, I believe, right? You must be given the new time, must have been, right? So on Wednesday, we will continue with learning more things about the periodic table. And please go through your periodic table before the trends and properties. Whatever terminologies which you do not understand, please feel free to ask. Because I don't remember whether I told you this fact earlier also or not, that periodic classification was a chapter of class 10. So whenever I teach or any teacher in class 11 teach, they have a certain inbuilt thing in their minds that, okay, the kids must be knowing, the students must be knowing about this, this, and this. But suddenly when you realize, okay, they are not taught all that, then although I try my best to keep the things from your 10th as well as 11th book intact here, still I'm a human being. I might have missed anything. So any terminology which you have not understood in class 10th, or it is not very clear, please feel free to ask me during the class, after the class, anytime, right? So see you on Wednesday, same time.
Ma'am,
We'll
I
talk
actually have a
more.
small question.
Yeah,
Ma'am, like how many chapters did you finish before this, ma'am? Like,
How
before
many?
today? Like
How many?
how many chapters did you finish, ma'am? Like before this?
We have done chapter 1, I believe. And chapter 2, I was asked to skip. So I
Okay,
have done
like are
chapter.
the videos available in the app, like chapter 1 classes?
You have to check with the coordinator, whosoever is there at the learning center. You just need to
Okay,
ask
ma'am.
them. Okay. In the meantime,
Okay,
I will just
yes, ma'am.
also push your query to them. They can explain to you. Right?
Yes, ma'am.
Anybody
Thank you.
having any other question?
No, ma'am.
Okay. So good. We'll see you day after tomorrow. And I'll again ask you to go through your chapter, the second half of your chapter 2, the structure of atom, where you talk about the configuration and the exceptions, right? Then move to your class, the chapter 3, read it till the point they have talked about the atomic size and all those things. Before that, please go through that and we'll be taking up in the next class, right? So good night and good evening and have a good day.
Thank you, ma'am.
Welcome.